Good afternoon, everybody. Welcome to this week's edition of the joint quantum computing seminar series that is a joint between Duke University, NC State, and UNC Chapel Hill. This week, I'm your host. My name is Eric Geisels. I'm a professor of economics at UNC Chapel Hill and a professor of finance at the Kenan-Flagler Business School, and the faculty research director of the Rethink Labs, which is co-organizing this. It's not very often that we actually have purebred economists in this seminar series. And our speaker today, Jesus Fernandez Villaverde, is the purest of the purebred economists, if I may say. And for anybody who sort of does a PhD in economics, goes through this sort of graduate program, they know that the first year of the PhD program is typically, at least for macro people, grinding through dynamic programming problems, getting the theory all right, and in particular then applied to economic models, solving economic dynamic equilibrium, stochastic general equilibrium models in particular. And today's speaker is really an expert on this. I am delighted that the profession actually is starting to pay attention to the possibilities of quantum computing, and I'm really looking forward to this talk. Jesus is a professor of economics at UPenn, and he's the director of the Penn Institute for the initiative for the study of the markets. He is really, truly a world expert in this topic. Jesus, it is great to have you. His co-author on this paper is Azaya Hull, who was one of the first speakers in this series as well. So welcome back, Azaya. Jesus, it's all yours. Thank you.
Thanks a lot for inviting me. And yes, I am. My goal today is telling you a little bit about how to do dynamic programming on a quantum annealer, and in particular, how to apply to solving the real business cycle model. And don't worry, I'm going to tell you in a second why this is important and what is the goal. So if you are in economics,
can I briefly actually interrupt, because there's one thing I forgot to say, housekeeping. So if you have a clarifying question, I apologize, Jesus.
That's okay.
If you have a clarifying questions, please feel free to put it in the chat, and then we can sort of respond in real time. If you have deeper questions, more, sort of elaborate questions, we'll address them at the end. You can still write them in the chat during the talk. And again, sorry, Jesus, for interrupting you on that.
Of course.
Go ahead.
Okay, thank you. So in economics, we tend to build models and to answer what we think are interesting questions. And this type of models often involve at least one of the following three things. First, these models are very highly nonlinear. So think about, how do financial crises arise? Well, this is nearly the perfect example of something that is very nonlinear, because the economy is kind of going smoothly and then suddenly you have a very quick crisis. Think about the models that economists use to try to understand why countries or firms default, or why firms invest in large lumpy projects. In economics, we also use something that is called models with heterogeneous agents, which means models that have a lot of different agents, a lot of different firms, a lot of different households. And we use these models to think, for instance, about what drives the changes in income and wealth inequality, or whether there is a trade-off between inequality and economic growth, or how does inequality affect monetary and fiscal policy. And last, we also write models with many, many state variables. By this, I mean models, for instance, that have many discrete nodes. So these days, economists are very interested in having models of climate change and how the climate change interacts with economic activity. And we want to think about geographical locations as a node. So we want to think about North Carolina as a node, and another node will be Pennsylvania, and another node will be Vermont. So you have models with all these different nodes that imply that you are going to solve models with a lot of state variables. But that also happens, for instance, when you are dealing with corporate finance, with models of the life cycle of households and firms, etc. And often all these three elements come together. As soon as I finish this talk, I need to go back and work on a paper with another set of co-authors where we are dealing on a heterogeneous agent model with nominal frictions, which make it very, very nonlinear, and many assets, which has many state variables. So what is the problem with this class of models that economists are interested? Well, that except in very, very rare occasions, these models rarely have our analytic solution. And then we need to resort to numerical techniques to solve it. We go to the computer and we try to compute the solution to these models. And we want solutions, of course, that are both accurate and fast. And by fast, economists usually think about both the running time. And today I'm going to report running time because it's the only thing you can really measure carefully. But we also care a lot about solutions that are not too difficult to code, in the sense that there is no point in spending 3 years coding something if at the end of the day, it makes too difficult the real analysis of the model. Now, most of the models in economics can be tackled with standard dynamic programming techniques. And those include, for instance, value function iteration, policy function iteration, or some combination of both. Nonetheless, and unfortunately, it is well known, and Richard Bellman himself in his pioneering monograph about the use of dynamic programming in applied math mentions it in the introduction in page 7, if I recall it correctly, talks about the course of dimensionality. Basically, the fact that as soon as we start having more than 3, 4, or 5 state variables, for all practical purposes, solving dynamic programming becomes really, really hard, if not impossible. And the same idea applies to other solution methods, such as perturbations, which are also very common in physics, but are also very applied in economics, or projection methods, such as Chebyshev polynomials. So what have economists done to try to tame the course of dimensionality? Well, we basically follow 3 strategies. The first strategy is we want to have better numerical algorithms. So if you go to my webpage, you will notice that over the last 4 or 5 years, I have written around half a dozen papers on how to use deep learning to solve dynamic programming problems. And I just cited over there one of those papers. That's good, and it works very nicely. A second possibility, and it's not a substitute, it's a complement, is to have better software implementations. And in particular, these days, I'm, for instance, looking in some detail into the advantages of functional programming and flexible data structures, because those allow much more easily for massive parallelization. And I'm doing this with a student with Zemlichka. And the third strategy is to have better hardware designs. Around 15 years ago already by now, I was one of the first economists who worked on introducing graphic processing units in economics. And just very recently, a few months ago, I circulated a paper where I show how to use field programmable gate arrays really helps a lot in economics. So you can think about our investigation today as belonging to this third strategy. Okay, so we investigated GPUs, they work very well. We investigated FPGAs, they work very well. Can quantum computers also do something good for us? And in that sense, I'm going to show you a proof of concept of quantum hardware, which I think is going to have very promising results. There is also, however, a flavor of the first strategy, because taking standard dynamic programming to a quantum computer, a quantum hardware, and trying to do it in an efficient way involves thinking a little bit about how you formulate algorithms about this fact. Okay. So the reason Isaiah and I got interested in this thing is because we became aware that universal quantum computers offer a theoretically provable quadratic reduction in the time complexity for dynamic programming, which means that at least in principle, we can really achieve incredible speed ups in the type of things that we can do, and then tackle all the type of problems I was mentioning before. However, this is a theoretical result, and because of two reasons. First of all, the way in which some of these results are set up are not directly applicable to many problems in economics. And second, because the current universal quantum computers just don't have enough qubits at this moment. If memory serves me well, the limit is 127. Maybe there is a new computer now with a little bit more qubits, and this is just not enough to actually implement any of these things in real life. So we decided instead to look into quantum devices such as quantum annealers that are closer to maturity and allow for experimental speedups. And quantum annealers these days have as much as 5,000 qubits, even a little bit more, so you can actually start doing this a little bit in real life. So what is our contribution? I'm going to take a model. It's going to be called the real business cycle model, and don't worry, I'm going to try to tell you what this is. But at this moment, suffice it to say that if you're a graduate student in economics, and we are starting the fall semester, I will bet you a lot of money that in all top 25 PhD programs in the United States, students are going to encounter this model in the first semester, and they are actually going to be asked to do a homework where they need to solve this model using a computer. So in that sense, I'm taking absolutely the fundamental model that macroeconomists use to start organizing their thinking. And I'm going to say, well, instead of going and writing this in Python, as most graduate students are going to do, and run it in my laptop, can I take it to a quantum annealer? And as I was mentioning before, what the challenge is going to be is that we need to rethink the algorithm that we use to solve this problem to achieve near minimum execution time, given the physical limits of the device. And that's why we are going to propose what I think are in themselves interesting new algorithms for dynamic programming. And what I'm going to demonstrate is order of magnitude speedups on quantum annealers over the best classical solutions. So a few years ago, I brought with Aruoba a paper where we basically take exactly this very same model as a beautiful test bed of computation, and we kind of implemented a state-of-the-art value function iteration in many different languages, so we have a very nice benchmark to compare our results against, and I'm going to show that, in fact, we do better than we were able to do in 2015, of course, running the same code of 2015 in a state-of-the-art machine today. Okay, so I was told that all of you are familiar with quantum computing, but just to be on the same page with respect to what quantum annealing is just a specialized quantum computational device that is aimed at solving the combinatorial optimization problem, which we know is an NP-hard problem on a classic computer. And basically the reason why quantum annealing works is because it's going to be a heuristic or finite temperature version of adiabatic quantum computing. So if you remember, basically what we are going to have in that situation is we are going to have an initial trivial Hamiltonian when we are going to have a superposition of all the states, and we are going to travel toward the minimum energy configuration of a Hamiltonian, and we are going to build this Hamiltonian to encode the combinatorial optimization problem. And of course, this is where the challenge is going to be. How do I set up my dynamic programming problem as a combinatorial optimization problem of the final Hamiltonian that I want to achieve? The very good thing about these quantum annealers is that they can return candidate solutions in milliseconds, and in particular, they can take advantage of quantum tunneling to escape local minima. So if you recall, basically, quantum tunneling allows the states to travel through small barriers that may be very high, but very thin. And that's actually what happens in economics all the time. So I have been solving these minimization problems for decades, and something I have learned is that you have a lot of these local minima that are surrounded by vertical and thin areas of higher value of the objective function. So the fact that you can tunnel through those is really extremely useful. I have been highlighting already that you need to encode this in the right way. And in particular, you must encode the parameters of the combinatorial optimization problem in a quantum system. And to do that, what you need to do is to map the objective function to a binary quadratic model, such as the Ising, or in our example, and don't worry, I'm going to tell you many more details later on, into a quadratic and constrained binary optimization QO. Okay? And that basically implies that the variables that we need to deal with must be binary, and the order of the terms that we are going to deal with must be quadratic or lower. For instance, if we are going to deal with variables x1 and x2, we can include those in our encoding, but we cannot include x1, x2, and x3. So we will need to think about quadratization techniques to get a representation that is sufficiently close to what we are looking for. Now, if you take network problems, those network problems have a natural formulation as a binary quadratic model. But these network problems are not that common in economics. Now, I need to be careful. If you are doing game theory, you tend to have this type of network problems. If you are doing some type of operation research / optimization of production, which is, in the borderline of economics, you also have these BQMs. But the standard dynamic problems in economics, or at least in macro or in microeconomics or in industrial organization, do not have this form. Which means that what we are going to do later on in just a few slides will be to map dynamic programming to the objective function, to an objective function, convert it to binary, so we can set it up in the QO and quadratize higher order terms. Okay, so this is the challenge. Okay, so so much for the introduction. Do we have any question now?
No, I think so. We can keep going.
Okay, so let me get then. This was kind of a motivation of what we are doing. So let me tell you what we are going to do in more detail. Okay, so the model I'm going to take is the so-called real business cycle model, which, as I highlighted before, is a major workhorse of modern macroeconomics. What I'm going to present today and what we are going to use as a test bed is a very simplified version. But if you actually go and look at the models that are used, for instance, by the Federal Reserve System in Washington and by central banks all around the world, are nothing but slightly more sophisticated versions of this model. So if you know how to solve this model, to a very large extent, you also know how to solve the much more complex models that are used for actual policy advice. And as I was mentioning before as well, if you are interested in models about climate change, for instance, you will also work with a slightly modified version of this model. There will be other layers, but at the end of the day, the mathematical structure of what we are going to do is very simple. I'm going to take the version of this model that I used in my paper before, that I mentioned before, because in that way, we can facilitate comparison with existing benchmark solutions. So what do we have over here? In this model, what you have is an agent that is solving a dynamic optimization problem. We usually call it a social planner. And the idea over here is that this social planner is going to maximize the expected discounted utility. Okay? So this is an agent that wants to maximize the utility it gets from consumption. And we can think about many utility functions, but in macroeconomics, we think there are good reasons to believe that the log utility function makes sense. And then you discount the future with beta that is less than 1. So this is well defined. And you sum from 0 to infinity. And don't worry too much about the infinity. Even if t is large, there is a well-known result in optimal control theory called the Turnpike theorem that says that for all practical purposes, the solution when t is large and infinity are roughly the same. And this social planner is going to take capital and is going to produce a final good with that capital, and there is going to be a curvature alpha that captures the idea that they are decreasing returns to scale in capital, and it's going to be subject to some productivity, to some technology. And I will tell you in a second how that technology evolves. And then to that production of the final good, you also have the undepreciated part of capital, where delta is going to be the depreciation, and you can use that output plus undepreciated capital either to consume or to have capital tomorrow. And you can see now where the trade-off is. I need to decide, this is on the right-hand side of this equation, I have the resources of society, of this problem. I have my production and I have my capital. And I need to decide how much of that I'm going to eat and how much of that I'm going to save for the future. And now you can see why this is kind of the fundamental problem in economics of consumption saving decisions. I mentioned before that we are going to have a productivity level, a technological level ZT, and what we are going to think is that this ZT belongs to some set, zeta, capital Z, and is going to evolve randomly given some transition metrics. And the idea is that technology evolves randomly. Sometimes it goes up, sometimes it goes down. Literally going down doesn't mean that we forget stuff. It means really that we are growing and that we grow at a lower rate than in normal times. And this is why this model is called the real business cycle model, because real means that we are having changes in our real technology, in how good we are at producing stuff, and that is inducing fluctuations. And macroeconomists have come to the agreement that this type of shocks are a very important component of business cycle fluctuations. And that's why this is such an important model. A is very simple. B, it highlights the choices between consumption and investment. And third, is not an unfair description of a lot of the things we see out there. Okay, so how do we tell the first year graduate students to solve this model? Well, what we explain is that you have a recursive formulation of this problem as a dynamic programming problem in terms of a Bellman equation. There is going to be a value function, V. Oops, no. It's going to be a value function V that depends on the two states, capital and productivity. Okay, and remember what I was telling you about having models with many states. As soon as we extend this model, instead of having two states, we can have 10, 20, 30 states, and that's why it's so difficult to solve these Bellman equations in real life. And then you have the return today, and you have a continuation. And the continuation, you have the discount factor that we have before, and we have the expected value function tomorrow, where the recursive notation means that I drop the t's, and what I have is a prime, which means the value of that variable tomorrow. And this is the expectation, of course, conditional on z, because z prime depends on z today. I'm going to define final output as just what I produce. Remember, technology times capital to the power of alpha. Now, solving this value function does not have a known solution, except in a very peculiar case, when delta is equal to 1, when the depreciation is equal to 1. Now, this is not very realistic because this is a lot of depreciation. Basically, it means you use your capital once and it completely disappears. But, and I could tell you later if you want why this is the case, when delta is equal to 1, we know that the optimal consumption is just a fraction 1 minus alpha beta. Remember, the beta is over here and the alpha is over here of your production, y. Capital tomorrow is the complement, alpha beta times y, and the value function is a constant, which is a complicated function of alpha and beta. I just didn't put it over there because it uses half the slide, and this coefficient over here on the log of y. So why are we going to look at the case where delta is equal to 1? Because this is going to give me an exact solution. So when I go to the quantum annealer and I get a solution, I can compare the solution I get from the quantum annealer against the theoretical benchmark. And if I say, well, this works well, then I have trust that in the case where delta is different than 1, the solution that the quantum annealer will give me will also be good. Okay, you always test these numerical algorithms in a case where you know the answer, and then trust that the answer will also be accurate in cases that where you don't know the answer. So you need to calibrate this model. And again, I'm going to follow the calibration I have in my own papers in the past. And suffice it to say that this is a very standard calibration. Okay, so we are picking absolutely normal parameter values. The discount factor is 99%, which means that you discount the future at a 1% rate. Think about this like an annual quarterly discount that will be around 4% a year, which is, roughly what we think the rate at which people discount the future. Alpha, the curvature of the production function, is 0.33, which matches the evidence we have from the data. And the only odd parameter is delta equal to 1, because remember, we want to have this closed form solution. In the real world, delta will be more like 0.1. Okay, so we are making delta 10 times larger than what it should be. And productivity is going to have 5 values. The average is going to be 1, and sometimes productivity is going to be higher than normal. Sometimes productivity is going to be lower than normal. And it's going to evolve according to this transition matrix. And these two values, this set of 5 values and this transition matrix, are estimated from the data of productivity in the US economy to match the properties of productivity in the US economy. Okay, so these things are based on something. Okay, so what is the solution method? Remember, I told you that this will be a standard homework for first-year graduate students. Well, what I tell my graduate students is Z is already a discrete state variable. So what I do is I also discretize K. And once you have both discrete values for K and Z, you can perform either a standard value or policy function iteration, or some mix of the two, using a standard lookup table. You have a current value for the value or the policy, you maximize, you get a new table, and you do that until convergence. It is known as a classic result that discrete dynamic programming has a space complexity big O of 1 over e to the power of d, given d grid points. And now you can see why this is a problem for us as economists. Because if you have many, many state variables and you want to have just a few grid points in each dimension, d is going to grow exponentially, which means that since this is in the denominator, you will have a very big O bound. But it's also a problem for trying to take this problem to a quantum software, quantum hardware. Why? Because the quantum to classical bottleneck reduces output to around 5,000 bits of classical information. And to get a good answer in terms of accuracy of the real business cycle problem, you will need around 285 times as many bits to have a decent lookup table. So this cannot really be done. So what can you do? Well, it turned out to be the case that in economics, nonetheless, we want to move away from value or policy function iteration because in practice it's too slow. And for instance, a few years ago, Benítez Silva and his co-authors proposed something called parametric policy iteration, or PPI. This is very similar to a lot of things that are also done in engineering. You may be familiar with ideas such as approximate dynamic programming, and it's, at the end of the day, it's roughly the same. PPI has a lower time complexity than discrete policy iteration, but may have worse convergence properties. Okay, so what we are going to do is the following. We are going to first solve a standard PPI on a classical computer. Okay? That will give us a benchmark. We know how long it takes, and we know what the answer is. And we can compare it, remember, against the exact answer that we already have. Then we are going to rewrite the PPI as a pseudo-Boolean optimization problem. That pseudo-Boolean optimization problem happens to be a combinatorial problem. So we are going to call that the combinatorial PPI. And we are going to solve that combinatorial PPI also on a classical computer. Why are we doing that? Because in that way, we have the standard PPI on a classical computer and the combinatorial PPI on a classical computer, and I can ask how different are the two solutions? How much I'm losing in terms of accuracy from moving from a standard PPI to a combinatorial PPI? And our answer is going to be not a lot. So a combinatorial PPI is a good way to think about a standard PPI. And then we are going to run the combinatorial PPI on a quantum annealer. And we are going to do first a hybrid classic QA algorithm. And we are going to see that there is a lot of promise, but that there is still some gains that we can achieve. And then, and at the end of the talk, I'm going to propose two alternative algorithms that build on our combinatorial PPI, make it a little bit better, and really deliver much better results. Just as a small note, the quantum annealer, we are going to use one of these D-Wave systems, 5,000 qubit quantum processors. Okay, and you can go to, you are probably familiar with D-Wave, but you can go to their webpage and take a look at what they do over there. Okay, so what is this PPI?
Jesus, may I ask a very quick question?
Of course.
In your transition matrix, you kind of had precisions up to like 5 digits or 4 digits. Yeah, there we go. Does it matter? That precision? Okay.
No, not really. We just do those precision because that's what we do for the classical setup in my 2015 paper. And we want to convince you that even with this high precision, we are going to nail this down very well.
Fair enough. Thank you.
We want to be cautious. We don't want to oversell any of our results. Okay, very good. So what is the standard PPI on a classical computer? So what you do is the following. You say, well, instead of having a discretized version of the policy and the value function, what I'm going to have is a parametrization of them with like a very simple parametric form. I'm going to initialize the parameters of that approximation in the case of the policy function xp and in the case of the value function xv. I'm going to use bold to denote the fact that they may be a vector and not just one parameter. And then fixing the parameters of the value function, some initial guess, I solve for the optimal policy function, and in the very next slide, I'm going to show you how you do that. And I get a new update of the policy function parameters. I plug in those policy functions parameters in my, excuse me, there is like the phone is ringing in the back. In my value function, and then I minimize with respect to xv, and I keep doing this until the Corbeil's criterion is satisfied. Okay, so it's basically I solve first for the policy function, and then I solve next for the value function. So how do you do this in this very simple problem? Well, you kind of take advantage that there are some results that suggest that the policy functions are going to be linear or quasi-linear in output. We actually know that when delta is equal to 1, that result is exact. And we are going to parameterize those k prime as k x1y and consumption as 1 minus x1, sorry, remember y, remember that they need to sum to 1. And for the value function, we are going to parameterize it in terms of x2 plus x3 log of y. And then we define the loss functions. So what are those loss functions? Those loss functions, again, remember, in the case of the policy, we take the x2 and the x3 as given. And if you notice over here, this is just the Bellman equation. This is the right-hand side of the Bellman equation. Okay? And on the Bellman equation, I want to minimize the Bellman equation. Well, I want to maximize it, so I put a minus, so I'm minimizing, and I'm going to minimize it, in this case, with respect to the optimal consumption. That's why I'm looking over the optimal x1. So that's the sense in which this is a policy function. I'm looking for the x1 that makes the right-hand side of the Bellman equation as large as possible. And then, when I want to improve my value function, my policy valuation, what I do is I say, this is the right-hand side of my Bellman equation, and this is my left-hand side. So I'm going to make a distance between the two, and I'm going to take a quadratic distance. And I'm going to select the x2 and x3 that make that distance as small as possible. Okay, and I keep just iterating. So I pick x2 and x3, I find the x1 that makes this as small as possible, and then given that x1, I pick the x2 and the x3 that make this as small as possible, and I keep going back and forth. And coding this and running this in either C++ or Python is extremely easy, is very fast, takes no time whatsoever. So that's what you do, in your homework, first year macro, okay? You go to the graduate students, you tell them about this PPI, and you send them back home, and you say, on Monday, you had in the Python code that does this. Very good. The problem is, you cannot take this standard PPI to the quantum annealer because it is not a combinatorial problem. What we need to do it is to reformulate, as I mentioned before, as a pseudo-Boolean problem. And what we are going to do is remember that this depends on our ability to find x1, x2, and x3. Well, what I'm going to do is I'm going to map the x1, x2, and x3 into binary variables. How do I do this? With this very easy Boolean function where the x sub mu sub j sub nu is just going to be either zeros and ones. These are going to be twos. And s nu is just going to be a scaling parameter such that x belongs into the appropriate interval. So for instance, we know that x1 needs to be between 0 and 1 because it's the amount of output that you are deciding to save. Cannot be negative, but it cannot be more than the total amount of output. Okay, so if you want to express the number 17, this is the way you will do it into this binary. And you can do this with any value do you want from the x1, x2, and x3. And that basically means you can represent using n of these j's with log 2 base 2 of n qubits. And if the only thing you want to do is minimize some function of the x's, literally, the only thing you need to do is check every possible combination of x sub nu sub j and just pick the combination of x sub nu sub j that minimizes your objective function. So it's going to be brute force. I have all these x sub nus, just let me check all of them and see which one minimizes my problem. Now, what I need to do is a little bit of effort. And in particular, I use a single set of binary variables to represent the x1 and two set of coefficients to transform them into log of x1 and log of 1 minus x1, because that's what I'm going to need to put within my objective function. And you have these expressions over here. And that means I can write my policy improvement. Okay, so remember, going back a little bit, this was the policy improvement before. The policy improvement was, I'm going to pick my x1s such that given my x2 and given my x3, the right-hand side of my Bellman equation is as high as possible. And why do I want to do that? Just to remind you, because this is what I want to solve. I want to maximize the right-hand side of my Bellman equation. So I go from this to here, and from here to here using pseudo-Boolean functions, or Boolean functions. And I can see the same for policy evaluation. Policy evaluation is this thing over here, G of V. And remember, the policy evaluation just comes because I want the left-hand side to be as close as possible to the right-hand side. So I'm actually doing it this right. I'm solving the dynamic programming problem. And since I'm not going to bore you too much about it, I'm going to have more than quadratic terms over there. I'm going to have this quadratization. There are different ways to do it, but this is going to work fine. And what I have at the end of the day is a combinatorial PPI. So I know I did some algebra, and these expressions, I know there is what, 1, 2, 3, 4, 5 summatories in just one line. So let's try to understand the intuition of what I'm doing, and then everything else will be absolutely straightforward. I'm saying, look, I have a dynamic programming problem in terms of a Bellman equation. That Bellman equation encodes both a value function and a policy function. I'm going to parameterize those policy functions and value functions in terms of a finite set of parameters. And I am going to express those parameters as binary variables. And then I'm just going to search for all the possible coefficients of those binary variables such that I minimize the objective function that is just the equivalent of maximizing the Bellman equation. I hope that you can see like the big picture of what we are doing. So now that I have set this up, the first question I need to ask is, does this work? Is this transformation from the original problem into a combinatorial problem going to give me an answer that is accurate enough? And the reason why this is going to be accurate or not enough is because I'm limited by the number of j's that I use. Okay, for 17, I get it right. But you know, if instead of 17, I have 17.349689, blah, 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 that will jump into the limitations of the j's, and the number of j's I can have comes from the number of qubits I have available in the quantum annealer. Okay, very good. So in fact, that's what we do. We initialize the value function parameters x2 and x3. We compute x1 analytically, because actually you can show that when you know x2 and x3, you don't even need to solve x1 numerically. And given this QO problem and x1, we perform the policy evaluation step by identifying the values of the coefficients in the binary variables that minimize the loss function. We map those back into x2 and x3. We go back to 1. We compute the x1 analytically, and so on until convergence. And this is what you get. Basically, it takes 67 seconds in a classical computer, but you actually only need 2 iterations. And this is a well-known property of PPI, that it converges very, very fast. And you can see here the relative errors of the x1, x2, and x3. And why do I know the errors or how big these errors are? Because recall that I'm solving this problem, and when delta is equal to 1, I actually know that x1 is, for instance, alpha beta. So I just compare whatever comes from the combinatorial problem against the solution of the computer. So what have I done so far? Let's recap. I have shown you how to write a dynamic programming problem as a policy iteration. And I have shown you how to transform that policy iteration into a combinatorial problem. And I have shown you that that combinatorial problem gives you an answer that in terms of error is extremely accurate. Well, now finally, we can go to the quantum annealer. What I'm going to do then is exactly as before. C over here is going to mean classical, Q is going to be the quantum annealer, except that instead of doing the minimization in the classical computer, I'm going to be doing the minimization in the quantum annealer. And I'm going to get new coefficients for the binary variables in each anneal. I'm going to map them into the value function parameters, and I'm going to compute the mean values that I get from the lowest energy level anneals, and I'm going to repeat these steps 2 to 5 times until the convergence criterion is satisfied. What is the beautiful thing between algorithm 3 and algorithm 2? That is basically the same algorithm, except that the step 3 over here is run on the quantum annealer. Sorry, over here is run on the classical computer. Over here is run on the quantum annealer. So you can really compare what is going on and check differences. So these are the results. What we are going to get is that the percentage error of x1, x2, and x3. Of course, since this is going to be an annealing, the results are random, it's going to be pretty good. We are going to make errors of the order of 5% for x1, 0.86 for x2, x3 is 832. And if you actually look at the mean, these errors are really very, very good, with a reduction of the total energy of 88%. And these numbers, sorry, I need to remember you that they are in microseconds. It's actually telling you we are doing this quite fast. In particular, it's going to require 1.83 seconds on average, which is 30 times faster than classical combinatorial PPI. Okay, so remember, I run my classical combinatorial PPI first on a classical computer. I can do this 30 times faster on a quantum annealer. On the other hand, I'm paying a huge overhead of going back and forth to the quantum annealer. And that means that this combinatorial PPI is going to be 2.5 times slower than a very simple value function iteration when I compute it with C++. So that means that this is a good result, but I'm not as excited as I would like to be. And in particular, what I notice, or what Isaiah and I notice, is that only 2.8% of the execution times comes from the QPU computation. So can we eliminate costly QPU reprogramming and transfer overhead and do it much more efficiently? And the answer is yes. So we are going to propose two new algorithms to do this, building our own PPI. The first one is we are going to call it a multi-anneal quantum PPI. As before, we are quadratize the policy improvement and evaluation pseudo-volume functions, except that now we are going to do it separately and reconcile the resulting qubits and then merge them. We are going to initialize the classical states of the policy function variables and the value function variables. We are going to initialize the xp and xv on the variables in the policy and value function. And then we are going to set an inhomogeneous annealing skeudel that first anneals over the x1s and xp's, and then anneals over the x2 and x3s and xv's. So this is the idea. Basically, we are going to anneal first over the policy improvement step, and then we are going to anneal next over the policy evaluation step. And then we just do a reverse annealing skeudel that applies to all qubits, and we do this n times without reinitializing the original classical state. And we just pick the results from the anneal with the lowest energy level. This is kind of a graph of what things are going to be updated and not updated, but let me skip that. And this is the really, really nice results. We still get very, very good relative errors. If you look at the mean, it's 0.18, 0.77, 0.48. But look at the QPU totals, we have gone to 1.86 to the power of 4, but these are to the exponent of 4, but these are microseconds. Okay, we have reduced this a lot. Over there, before we were 5.1. Now we are 186, which means that we are already competitive with value function iteration and C++, which is the very best thing that we know how to do on a classical computer. Okay, and now, in particular, what you can realize is that we are only using 0.028% of the compute time of a classical combinatorial PPI and 2.5% of the time of the value function iteration. That is, we can actually do this thing around 40 times faster than on a classical computer. And that's really very nice. So for instance, when I use FPGAs, I show that you usually get a speed ups between 40 and 50. So our quantum annealer is comparable in terms of speed with an FPGA. However, we have two limitations. First, that the total level energy is uninterpretable, and you may have noticed that over here in this table, I don't report the energy level, and that's because the XPs and the XVs, the variables in the policy and value function, converge to 0 over the annealing step, and because there is going to be a high degree of correlation across candidate solutions within a QPU execution, and we need to execute the QPU multiple times to get independent solution candidates. So can we do better? Can we improve the algorithm by allowing for multiple iterations over both the policy and value function within a single annealer? And the answer is yes. And that's the very last algorithm that I want to present today. I'm going to do it quickly and only give you the punchline that this is what we call a one-shot quantum PPI, where we do pretty much the same as we were doing before, except that in the middle, we set an inhomogeneous annealing skeudel to activate the policy improvement and policy evaluation functions in sequence, and to anneal their associated variables by C cycles. We are going to, you will see over here, for instance, we are going to do this in 3 different cycles. And that's going to allow us later on to set the global annealing skeudel to perform a full reversal, and we are going to do n anneals and reinitialize the state after each of that, compute alternative measures of terminal state energy for each anneal, and return the average parameter values over the lowest energy anneal. And we get these really, really nice numbers now that, you know, make us really very satisfied. Let me conclude, since I only have 1 minute left. In this paper, I think we have demonstrated as a proof of concept that quantum annealers can be used to solve dynamic programming problems like the ones we use in economics. And the approach is very simple. You reformulate your value function problem, your recursive problem, as a PPI, and you rewrite that PPI, that policy iteration, as a combinatorial problem. You send the combinatorial problem in terms of binary variables to the quantum annealer. The quantum annealer finds the values of those binary variables that minimize the Hamiltonian. You return them back, and then you have your very good solution. And I have shown you that that solution is very accurate, both with respect to the original PPI run on a classical computer and with respect to a standard value function iteration also run on a classical computer. So we have produced what I think is a set of 3 very interesting, novel, hybrid, and fully quantum algorithms, test them on the RBC model, and show you improvements in speed of around 40 times with respect to the best state-of-the-art C++/Fortran solutions. And these ideas that I told you, I just show them with the RBC, but at the very core, the idea is always the same. I have my value function problem, I solve it, or I recast it as a PPI problem by parameterizing the policy and the value functions. I rewrite it as a combinatorial problem, and I solve the combinatorial problem on the quantum annealer. Thank you.
Wonderful, Jesus. Very clear presentation, very pedagogical. Thank you. We have a few questions, and I don't know whether you have access to the chat.
Yes, let me open.
Pierre Minson has a question about what is the range of n number of annealing to ensure you'll have an acceptable error on each variable? Okay, so I don't remember now from the top of my head. I think we were doing around 10 this time. And we were surprised that the standard deviation was not that high, so we didn't feel that we needed more than that. I forgot to mention, the paper is already written. The only problem is we only need to, actually I was waiting for this presentation to figure it out if there was something that I needed to explain a little bit better. We hope to have a working paper in 1 or 2 weeks posted on my webpage, and I imagine that Isaiah will also post it on his webpage, and we will also circulate it soon as a National Bureau of Economic Research working paper. So in that sense, all the details will be available to the profession at large, and I will be happy to post these slides on my webpage. But over there, I have the details. I think that the number of anneals we do is not that high, and that we were satisfied that that low number was good enough. Yeah, the next, thanks. And I'm actually looking forward to that paper.
Yeah.
previous question was kind of a real-time question, maybe clarification. Can you remind us how many iterations it takes for the convergence on the quantum annealer?
A very few. And again, I guess I should have, but for instance, over here, we only need to run 3 cycles. And let me stop the share over here because I have the paper also open as a PDF. And I think that over there we report that number. Okay, so we run the thing 50 times. So we run algorithm 4 50 times with 20 anneals. Actually, I can share the paper over there. Can you see it over there?
Yes, I can.
Okay. Yes. So we do 50 executions. Each performs 20 anneals. Okay.
Great.
And this is now the total time gets reduced to 0.018 seconds, which, you know, if you think about it, you know, have you told me when I was a graduate student that I will solve the RBC in 0.02 seconds? I remember a graduate student running this in Fortran and it will take like 5 minutes.
Right.
But that's also the case that back then computers were a little bit slower.
I know that you kind of look at your toy model, the one that sort of everybody,
Yeah.
I mean, there's the number of state variables, that's one thing. The Markov chain,
Yeah.
how much does that matter in terms of the number of states?
Oh, yeah, go ahead.
Yeah, that's my question, actually.
Okay.
So I mean, you know, you have the 5 states and their transition matrix is kind of quite well structured, but how does that matter in terms of the actual computations and the accuracy?
Okay, yeah, that's important. Okay, so first of all, let me be sure, because sometimes in macro we use the word state slightly different than in econometric.
Yeah, I apologize. Yes.
Yes. So by states, what I mean
No, I understand.
is the variables. Yeah, is the variables over here.
Dimensionality of the transition matrix.
Exactly. So this is going to matter for how good your model matches the data. So if you have only 2, like high and low, then the model is going to do a terrible job matching the data. If you have ZT of 11, then your model is going to really match the data of productivity very well. What this is going to matter is that the more elements you have in the support of the Markov chain, the harder it may be to compute this expectation.
Correct.
And that's going to make harder to get, when you are doing over here the PPI, is the harder it's going to be the combinatorial problem to get the x's. Okay, so this is not as much of a problem of the solution method. This is a problem of how accurate you want your model to be, and the more accurate you want your model to be with respect to the data, the heavier the computation. And of course, and I must highlight this, the reason we are calling this a proof of concept is because, you know, we are still, you know, 5,000 qubits is better than 127, but this is still 5,000.
I agree.
Okay, so the day that we have 5 million, then I will be able to have like many more state variables. Because, and by the way, this is something, I know that some of you are engineers or people from the natural sciences, and I remember because my engineering friends always think that the world has 4 state variables, which are the 3 Cartesian coordinates plus time. But in many problems in economics, I know that Mahdi, one of my best co-authors, is online right now, and we solve with him a problem that has 10,000 state variables. Okay, so economists routinely deal with problems that have 10,000 state variables. That's why we really, really want to be able to compute this fast. So if quantum computers in a decade allow me to solve this much, much faster than FPGAs or GPUs, the number of things I can do is really amazing. That's why, you know, that's why I got so interested in trying to solve this. And I have spent some time over the last year trying to learn a little bit about quantum computing. Of course, I don't really know much. I'm just a dilettante in this area, but this is why it's so exciting for me.
I'm in the same boat, Jesus. I'm also kind of learning and excited about this field, but my background is economics. By the way, we got one comment saying that people in physics also deal with 10,000 state variables.
That's fun. There may be engineers, but I know a lot of my friends.
We're not gonna start this fight.
Exactly. No, I'm just saying because a lot of my friends are in engineering, and my
right.
engineers friends always say, no, there are 4 state variables.
Right.
X, Y, Z, and T. That's it.
I agree. We are running out of time. Really, I really enjoyed your presentation. It was actually absolutely great. And thanks for presenting your work today. And I'm looking forward to your discussion paper coming out. And I'm saying also hi to Isaiah, your co-author, whom I will see in a couple of weeks.
Of course. And if anyone has any further question, please send me an email and I will be happy to answer.
Thank you. I wish you, all of you, good rest of the day and a good weekend. And please consult the website for all our future wonderful seminars in this series.
Thank you.
Thank you and goodbye. Bye-bye.